Good morning, students. Let us continue with Chapter 9 Force and Laws of Motion. In the sixth session today, we will learn what is conservation of momentum, its mathematical derivation, its statement, activities, and examples related to conservation of momentum. From the second law of motion, we already know that momentum equals mass into velocity. Here in the picture, we see in figure a truck of mass m1 moving with an initial velocity u1 and a car of mass m2 moving with an initial velocity u2. Let us assume that u1 is greater than u2, that is, the truck is moving at higher speed compared to the car. So, there is every chance that the truck might collide with the slow moving car for a time t seconds. After the collision, the truck speed will decrease, whereas the speed of the car will increase due to the transfer of velocity from the truck to the car during collision. It is observed that the total momentum before collision, that is m1 u1 plus m2 u2, is equal to the total momentum after collision, that is m1 v1 plus m2 v2. This is what we call conservation of momentum. Now we will prove this mathematically. As seen here in figure A, let us consider two balls A and B of masses MA and MB. They are traveling in the same direction along a straight line with different initial velocities UA and UB before collision. Here, we also need to note that there are no other external unbalanced forces acting on the balls. Here in figure B, let us suppose that UA, the initial velocity of ball A, is greater than UB, the initial velocity of ball B. Due to this, the two balls collide with each other for a time t seconds. During this collision, the ball A exerts a force FAB on ball B and the ball B exerts a force FBA on the ball A. Now, as shown in figure C, VA and VB are the final velocities of the two balls A and B after the collision. We know from second law of motion that momentum is the product of mass and velocity. So here the momenta of ball A before and after the collision are MAUA and MAVA. Students, please note, momenta means plural of momentum. So the rate of change of momentum for ball A during the collision is given by FAB equal to MA into VA minus UA by T. Similarly, the rate of change of momentum of ball B during the collision is given by FBA equal to MB into VB minus UB upon T. But we know, according to the third law of motion, FAB equal to minus FBA. And this is our equation 1, which means that the force FAB exerted by ball A on ball B and the force FBA exerted by the ball B on ball A must be equal and opposite to each other. On substituting the values for FAB and FBA, we get MA into VA minus UA upon T equals minus MB into VB minus UB upon T. This in turn gives us the equation 2 MAUA plus MBUB equals MAVA plus MBVB. As the total momentum of the two balls A and B before collision is equal to the total momentum after the collision, that is, MAUA plus MBUB is equal to MAVA plus MBVB. From equation 2, we observe that the total momentum of the two balls remains unchanged or conserved. So from this, what we understand is conservation means no change or remains constant. Now, let us define the statement. According to the law of conservation of momentum, the sum of momenta of the two objects before collision is equal to the sum of momenta after the collision, provided there is no external unbalanced force acting on them. Here, the picture shows an activity where a big rubber balloon is inflated and its neck tied up with a thread. A straw is stuck on the surface of the balloon. A thread is passed through the straw with both the ends of the thread fixed on two different walls. Now, if the neck is untied, we find that the air escapes to the left and the straw, which is in collision with the balloon, moves to the right. This is due to conservation of momentum. In this activity, a glass test tube is taken with a small amount of water in it and a stop cork is placed at its mouth. After suspending the test tube horizontally by two strings of wire, it is heated with a burner till the water vaporizes and the cork is blown out, pushing the test tube in the direction opposite to the direction of the cork. This is again conservation of momentum. Here in this example, the high velocity hot gases that come out downwards due to burning of the fuel imparts equal but opposite momentum on the rocket, causing it to move with high velocity in the upward direction. So, a rocket works on the principle of conservation of momentum. Similarly, a jet aeroplane also works on the principle of conservation of momentum with the hot gases moving backwards and the jet aeroplane moving forwards with a high velocity. That's all for today, students. Thank you.